Docker networking looks confusing at first, but once you see the actual path a data packet takes, it clicks pretty fast, and that's what I want to show you today, step by step, with real examples, not just theory. Containers are isolated by default. Think of a container as its own little box with its own network stack. It doesn't just borrow your laptop's network card and start talking to the internet on its own. Somebody has to build a road between the container and the outside world, and that somebody is Docker. When you install Docker and start a container without any special settings, Docker automatically creates something called a bridge network. This bridge acts like a virtual switch running inside your machine. Every container you launch gets plugged into this switch unless you tell Docker otherwise. And because they're all sitting on the same switch, they can talk to each other using their internal IP addresses. No extra setup needed. Here's a detail most tutorials skip. Docker actually ships two kinds of bridge networks. There's the default one, literally named bridge, and there's what's called a user-defined bridge, which you create yourself with a simple command. The default bridge does not give you automatic name resolution between containers. So if you have two containers on the default bridge, they can only reach each other by IP address, not by container name. But if you create your own custom bridge network and attach containers to it, Docker gives you built-in DNS. That means one container can just ping another by its name, like database or backend, and it works. This is a big reason experienced Docker users almost always create custom networks instead of relying on the default one. Now let's talk about how the container physically connects to your machine, because this part trips people up. Docker creates something called a virtual Ethernet pair, basically a fake network cable with two ends. One end sits inside the container and shows up as an interface called eth0. The other end connects to the bridge on the host side. So when an app inside your container sends data, it travels through eth0 across this virtual cable onto the bridge and finally out through your machine's real network card. Every container on this bridge gets a private IP address that only exists inside your machine. For example, your laptop might have a real network address like 192.168.168, while a container running on it might get something like 172.17.0.22. The bridge itself usually sits at 172.17.0.0.1, and it acts as the gateway, the exit door for anything the container needs to send out. Let's say you're running an Nginx web server inside a container and it's listening on port 80. There are two completely different journeys to understand here, and Docker treats them very differently, which is exactly why people get stuck. First, outbound traffic, meaning the container reaching out to the internet. Say the app inside needs to download something or call an external API. The packet leaves through eth0, crosses the bridge, and lands on the host. But there's a problem. That packet still has 172.117.0.2 written as its source address, and that address means nothing outside your machine. No server on the internet knows how to send a reply back to a private Docker IP. So the host steps in and rewrites the source address before the packet leaves, swapping 172.117.0.2 for your machine's real address, 192.168.1 Pandu. This is called NAT, Network Address Translation. To the outside world, it looks like the request came straight from your laptop, not from some hidden container. When the response comes back, the host remembers which container asked for it and routes it back correctly. This whole process is automatic, and honestly, it's the part that just works without you thinking about it. Second, inbound traffic, and this is where most beginners get stuck. You start Nginx, it's running fine inside the container, but when you open your browser and go to localhost on port 80, nothing loads. The reason is simple once you see it. That container's IP address is private, so nothing outside your machine can reach it directly, and by default, your machine isn't forwarding any outside traffic into it either. You have to explicitly open a door, and you do that with the publish flag when you start the container, something like -p 8080:80. That tells Docker any traffic hitting my machine on port 8080 should get forwarded down to port 80 inside the container. Docker sets up another NAT rule specifically for this, and now requests coming in on 8080 get redirected to your Nginx server. One thing that catches people off guard here: the app inside the container needs to actually listen on all interfaces written as 0.0. 0.0, not just on localhost or 127.0.1. If your app is only bound to localhost inside its own container, that forwarded traffic hits a dead end and you'll get connection refused even though you did the port publishing correctly. I've personally lost time debugging this exact issue, thinking my Docker setup was broken, when really it was just an app config problem. Beyond bridge networking, Docker gives you a few other network drivers worth knowing. Host networking skips the whole virtual cable and NAT setup entirely. The container just uses your machine's network stack directly. This is faster because there's no translation overhead, but it also means the container isn't isolated anymore on the network side, so you lose a layer of security. There's also a network mode called None, which gives the container no networking at all, useful for certain batch jobs that don't need to talk to anything. And if you're working with multiple machines instead of just one laptop, that's where overlay networks come in. Docker Swarm and similar orchestration tools use overlay networks to let containers on completely different physical machines talk to each other as if they were on the same local network. This is the same basic idea as the bridge, just stretched across multiple hosts using tunneling. Kubernetes handles this differently through something called a CNI plugin, but the underlying goal is the same, letting isolated containers or pods discover and reach each other reliably. A quick word on security, because people often forget this part. Every port you publish is a door into your machine. If you're running a database container and you publish its port to your public IP without thinking, you might be exposing that database to the entire internet, not just your local network. A safer habit is to only publish ports you actually need exposed and keep internal services like databases on a private custom network where only your other containers can reach them without any port published to the host at all. If you ever get stuck debugging Docker networking, there's a pattern to follow. If a container can reach the internet but nothing can reach the container, you probably forgot to publish a port. If two containers can't talk to each other, check if they're even on the same network, because containers on different bridges are isolated from each other unless you connect them manually. And if everything looks right, but you still get connection refused, check what address the app inside is actually bound to. Once this mental model clicks, honestly, most Docker networking problems stop being mysterious. It's really just two rules running under the hood, one that rewrites addresses going out, and one that rewrites addresses coming in, and your machine sitting quietly in the middle handling both directions.